Let's look at this problem. Now we have a uniform thin hollow square plate. Again, it has mass of m. And we need to determine its mass moment of inertia about the y-axis again, which passes through its gravitational center G. So we can see that this can be considered as a bigger square thin plate with mass of m1 minus a smaller square thin plate, the one that's in the center, even smaller, with mass of m2. Both of these two are solid. This one right here has a length of L, of the side of L. This right here has a side of 1/2 L. Both of them are squares. Both of them are solid. So one big solid minus another small solid gives us this shape right here. And also a good news is that this y-axis is also a centroidal axis for this big solid plate, as well as the same axis for the smaller M2 plate. So because of that, we can directly use this right here, that Iy, the mass moment of inertia of this body, this plate, simply equals to Iy1 minus Iy2. Iy1 is the mass moment of inertia of this bigger plate about this y-axis, and Iy2 is the mass moment of inertia of this smaller plate about the y-axis. We can do that directly without using the parallel axis theorem because these three axes are the same. So we're calculating the mass moment of inertia about the same y-axis. So from the previous problem, we have already determined that this general equation that Iy equals to 112 ml squared. This is the general equation that applies to these two solid square plates. Therefore, because this bigger plate has mass of m1 and side length of L, so Iy equals to 112 m1 squared times L squared minus 112. For the smaller plate, its mass is m2 and its side is L over 2 squared. However, what are m1 and m2? All we know is that the total mass for this hollow square plate is m, which means that we know m1 minus m2 equals to m. And because we have this uniform thin plate, it also means that the ratio between m1 and m2 equals to the ratio between their volume, but because they have the same thickness, that also means, so it means it equals to V1 over V2 because they're uniform, so rho, the density is the same. But because they have the same thickness, this also equals to A1 over A2, which means that that's the ratio of the total area of these two square plates. So for the bigger one, its area is L squared. For the smaller one, its area is 1/2 L squared. So this ratio right here is a 4:1 ratio. So in other words, m1 equals to 4 times m2. But m1 minus m2 equals to m. So when we combine these two equations, we can solve for m1 and m2 as expressed in m. So in that case, we can determine that m1 equals to 4 over 3m and m2 equals to 1/3 m. So we can solve for these two masses expressed by m. So now if we substitute them in, all right, m1 equals to 4/3 m, m2 equals to 1/3 m. We do the evaluation and we do the simplification. Eventually, we draw the conclusion that Iy equals to 5 over 48 ml squared.